Alright, so in this example, we've got a mass at the top of a slope here. It starts from rest, and it's going to slide down a distance d, and there is friction. We know the coefficient of kinetic friction is this mu here. So we want to find what will its final velocity be at the end of this slope. Okay, so we now are going to solve this using energy. And this video is for if you have not learned about potential energy yet, meaning the method we're going to use is we know that the total work is equal to the change in kinetic energy. Okay, so let's do a free body diagram of this mass while it is sliding down. We've got gravity, we've got normal force, and we've got friction. So in theory, any or all of these can be causing work, forces cause work, but since the direction of the distance is here, the angle between normal force and distance is 90. So we know that that normal force is not doing any work. In fact, normal force never does work. But friction and gravity should probably be doing work in this case. So the total work would be the work done by friction plus the work done by gravity. And that's going to be equal to the change in kinetic energy. So that's 1/2 mv final squared minus 1/2 mv initial squared, right? But we said initial velocity was 0, so that zeroes this whole term out. Okay, so we're looking for this final velocity, which is right here in my kinetic energy term. So if I can figure out what these works are, then I should be able to solve for velocity. Okay, so in general, work is, let's see, over here, maybe I was right. Note that work is equal to a force times a distance that it's going times the cosine of the angle between the force and the displacement. So let's do it. The work done by friction will be equal to the force of friction times the distance times the cosine of the angle between them, and that angle is 180 degrees. Now the cosine of 180 degrees is -1, so this simplifies to negative force of friction times distance. Okay, but we don't know the force of friction exactly. We do know, though, that the force of friction is mu times n, right? And so I can rewrite the work done by friction as negative mu times n times the distance. But we don't know the normal force, so we just keep plugging in here, right? We don't know the normal force. We have to find that. So the way that you always find normal force is with the sum of the forces in the y direction from my free body diagram. This is the y direction, and this is the x direction. Okay, now the sum of the forces in the y direction will be 0 because it's not moving or accelerating in the y direction. And that's going to be equal to normal force in the positive y direction minus this piece of gravity, the y component of gravity. Okay, now we don't actually know the y component of gravity, but we do know that the angle of the slope is theta, and that means that this angle here is theta as well, which you can prove to yourself with a little geometry. So, let me just move this. This is the force of gravity here. Using right triangle trigonometry, we know that FGY is equal to FG cosine of theta. So, and you can prove that to yourself, I believe. So rearranging this, we get that n is equal to the force of gravity times the cosine of theta. So I can plug that in here. So the work done by friction is negative mu force of gravity times cosine of theta. Recall that the force of gravity is just mg. So normal force is mg cosine theta. And then times the distance. Okay, so we found the work done by friction. Now let's find the work done by gravity. Okay. So the work done by gravity should be the force of gravity times the distance times the cosine of the angle between them. Okay, so the angle between gravity and distance is this, right, the gravity and the distance, and that is going to be 90 minus theta. If you look at this triangle here, this triangle here, okay, we've got a 90-degree angle, theta there, and that makes the angle up in the corner between gravity and the slope of the ramp 90 minus theta. So I should actually put the cosine of 90 minus theta. All right. And 90 minus theta is the angle between the gravity and the distance. And we know that the gravity is mg, right? So force of gravity, mg cosine of 90 minus theta, like that. So we found the work done by friction and the work done by gravity. So plugging these into my first equation, I get plugging into this equation up here, we're going to get the work done by friction is negative mu mg cosine of theta times d. Oh, I forgot my d right up here in my work done by gravity. Okay, plus the work done by gravity, which is d mg cosine of 90 minus theta, and that's equal to, up at the top here, 1/2 mv squared. Okay, we have an m everywhere, so we can divide through by m and solve for v. Multiply both sides by 2, take the square root, and we get that v is equal to the square root of, let's see, and I don't know, I could factor out 2g from that side, 2g d for that matter, cosine of 90 minus theta minus mu cosine of theta. So just a little bit of algebra in that last step. Alright, so because we don't know potential energy yet, this is the method that we used. We started with the work energy theorem. Total work is equal to the change in kinetic energy. We listed out all the works and the definition of kinetic energy and solved for V. Really, the most tedious part was just figuring out the work. The general equation for work itself is rather simple, but it can get a little annoying when you have to find what the force is. So for the force of friction, we had to do all this. We had to find the normal force so we could find the force of friction. And you also have to find out what is the angle between the force and the distance, and that can be a little tedious at times as well. So for the angle between gravity and d, for example, was 90 minus this angle that we called theta at the beginning. All right, and that is it.